And we sort of settled for this loss function. We know that that differs from the prediction loss of Akaike by a sort of constant in the sense of not depending on alpha. It's a random variable, but both the random variable depends on the parameters, but doesn't depend on alpha. So the object is to do as well as alpha L that minimizes this. I also showed you the rules that are, no, where did I show you that? Oh, here. I also showed you the rules that have been considered by Jun Shao, these so-called penalized log likelihood rules, except that these are better interpreted now because of change of signs. Think of Sn alpha as some sort of goodness of fit, or what Professor Zellner called goodness of fit, how well the alpha model fits the data, so Sn alpha. But once again, if you choose a very complex model, you can fit exactly all the data, and the second term is a penalty for that. So in this context, the log likelihood becomes minus log likelihood is a goodness of fit quantity, and the second term is a penalty. There's one thing that I should probably have mentioned earlier but forgot to, is if you ask yourself how would these two penalties do, Akaikes and BIC, you can see they're very, very different. That's why there has been two camps following these two penalties, two penalty coefficients, so to say. This penalty is so large that it will tend to choose very simple models. This is penalizes much less, so this will tend to choose more complex models. We'll come back to these later. These intuitions can well, these are not intuitions, these are trivial facts, but to associate these, so this has been extrapolated to Bayes rules in Akaike. So Bayesians have often felt that they tend to choose smaller models than Akaike. That's not right. We'll come back to these. And the fact to remember is that the BIC is only an approximation to the Bayes factor under certain conditions. So I've shown you the optimality. Now maybe here's the theorem. So here's, when you say that you do as well as alpha L, you might mean one of these two conditions. This says that your model selection rule, anything that you propose, is equal to the loss of the oracle with probability tending to 1 under the true values. It's an asymptotic frequentist notion. Sometimes that causes problems, so you look at the ratio and you want this converse to 1 in probability or almost surely whatever. These are not Jun Shao's terms. His terms are very confusing. Jun Shao's paper had many discussions, like Rudy Barron of Berkeley, Marvin Stone of England, and other model selectors, John Rao's son, and who else, I forget. But they were all confused by the notion of, so that's the way I've avoided using his terms, but kept his notions. So A and C stands for correct. It's the base of all correct models. It might be empty. I said that sometimes it might be empty. And script AN is the space of all available models. And then the difference is AN minus n complement is the available false models. Here is a basic decomposition, and which would immediately explain why Akaike has a special role. What you have on the left-hand side is that penalized goodness of fit criterion, gamma n, lambda n, alpha, and we're looking at rules which minimize the left-hand side for some lambda n. Lambda n is something that you choose. It could be Akaike, it could be BIC's log n, or something else that you decide for yourself. What you have as the first term on the right hand side is this error, unobservable error, vector norm of that square over n. It's n01, but you don't know how to get that. Then you have ln alpha, the loss that we want to, our square error loss, and the oracle minimizes ln alpha. Then you have a term as a sort of remainder term, and plus something which is smaller order than ln alpha. This is true for under conditions. Under conditions, it's true for all alpha in the space of false models. Alpha n minus alpha n complement is the space of all models. So this decomposition holds uniformly true for all false models. Now focus on this term. Sigma hat n squared is close to sigma square, and if you take lambda n equals 2, then this term disappears. If this term disappears, then it's immediately clear, because of this decomposition, that at least asymptotically, minimizing the left-hand side is equivalent to minimizing ln alpha. The left-hand side and the right-hand side, namely ln alpha, differ only by norm of en square over n. That does not have any alpha in it. So even though ln alpha may be very different from the penalized goodness of fit criterion, it differs by something that doesn't depend on alpha. So minimizing one would be equivalent to minimizing the other, provided the term shown by my pen, that disappears, and that disappears only if lambda n equals 2. So indeed, for prediction loss and for such criterion, we're not using all criteria, we're using very special criteria, this penalized goodness of fit things. Lambda n equal to 2 plays a special role. And it's almost immediately clear that if all models are false, what Akaiki had said, the AIC is going to be asymptotically as good as the oracle. So that's the theorem. And the only conditions I need are conditions to ensure these. The conditions that Jun Shao have are somewhat, I would say, they're written down explicitly, but to understand them fully takes a bit of time. I might show you what they are, but I will not discuss them. Later I'll discuss an example. Let me see if I have. Oh, here's the theorem. That's the theorem that I was talking of. So we're looking at the case that I just discussed. The space of correct models is empty, so everything is false. And the condition that you need is what I've shown as star. I'll show you what Rn alpha is. It's basically the expectation of ln alpha. Rn alpha is expectation of ln alpha. And what you need is that for all false models, this sum goes to 0. That goes to 0 means for all false models, the risk is sufficiently large that each term goes to 0. For the sum to go to 0, each term has to go to 0. And it has to go to 0 sufficiently fast that if you have many, many models, in spite of that, the sum goes to 0. Each term goes to 0, the sum goes to 0. So that's the kind of condition it is. I said that Jun Shao did not assume normal models. If he had assumed normal models, we could take L equal to 4. I think that's what you need. And all that you need is some condition like this. Say, I'm sorry, you take L equal to 1.
Sir.
So,
Sir, ANs are finite?
What?
ANs are finite?
ANs are finite, but their cardinality can increase with n. In fact, ideally, you can think of triangular arrays. So everything depends on n, and they can blow up. Oh, here's Rn alpha. Rn alpha is expectation of ln alpha, and people who work on these frequentists try to motivate this in this way. That's what they call the bias, and that's the variance term. And people who do Akaiki and this kind of model selection, for example, Dr. Rao has done that too, has used Akaiki in He's done this in growth curve modeling. It's known that you don't use the most complex model, and the intuitive explanation for that is if you take a very complex model, the bias becomes small. Bias means this thing here. That means mu n is the true mean vector. That's the projection matrix to the alpha linear model. So that's the projection to the linear space of the alpha model. That's the bias square or whatever. Now if you take a very complex model, this of course would be 0, but then this dimension would increase and your variability would increase. So there's a trade-off between bias and variance that occurs in many frequentist calculations. In density estimation, for example, in frequentist density estimation. So that's the way that they try to motivate these things. And of course, in all of these, we assume that once you choose a model, and that's important, we use a least squares estimate. So that's the theorem that I was talking of. And I think by now you understand why Akaike has a special role. I said Junshao has also theorems about BIC and so on. So what it does is basically to look at that decomposition under the same conditions. That means all models are false. So if lambda n is not equal to 2, you must have conditions to ensure that this happens. So it's sort of a simple matter of accounting. It's a very illuminating theorem, but the proof is fairly easy. And the proof is based on an old inequality of one of the British probabilists, I forget his name, at Cambridge, about quadratic forms. But I will not get into the proof. I should also put a little bit more background. The result that I'm referring to is Junshau's has its roots in some work done in the late 80s by Ka-Chao Lee, who's also a very bright person like Junshao. And that's in the annals. And the notion of the oracle is already in Ka-Chao Lee, but the theorems are not so nice. So Junshao has made the theorems very nice and transparent. The proofs are also similar. So the use of these fourth moments, use of the inequality of this British probabilist, that goes back to Ka-Chao Lee. What's the relation to what Shibata had done? I don't have any transparency to show. For some reason, I thought I'm going to give you only 2 lectures. If I can write up, I'll show you tomorrow. The reason that I read Shibata's paper when, not when they came out, but later. But once again, I could follow his mathematics, but I could not follow why Akaike was doing well. I mean, I didn't get that intuition. And one of the difficulties was that now that I can see Junshao, I understand what he was doing. He had something like an oracle, but it was not easy to show that it's an oracle. So that itself required a long argument. So, the formulations are also different. What Shibata had was, in some sense, more realistic in a certain, especially in maybe in time series context. He had a function, take a function which is square integrable on 0 to 1. And then you look at nested regressions. That means you look at, for example, the Fourier transforms or any other set of orthogonal polynomials. And you want to approximate this function by a finite Fourier series or a finite series of orthogonal polynomials. So those are your models, this finite series, like polynomial regression. Now it's clear that it's just a square integrable function. It's not a finite combination. So once again, the true model is not in the model space. And he has theorems of this kind, but not with this oracle, something else which makes it more complicated. What happens when the space of available models is not, true models is not empty? Take a very simple case, P equal to fixed. If P equal to fixed, then Akaike, and suppose that the simplest model is true. Akaiki will not be able to locate that. Once the simplest model, what you look at, if the simplest model is true in the nested case, all the models are true. But Akaiki does not penalize enough to choose the simplest model. So it will choose one of the two models, but not the simplest model, which is what parsimony requires. So it's not going to work. But it works in some cases. If there's only the theorem that I showed you earlier, when all models are false, is also true under the same conditions, no extra conditions. If there's a unique true model. If there's a unique true model, then also it works well. If there's at least one correct model, then you need, if there are more than one correct model, then you need some conditions. I will not go into these. I mean, they're not hard to guess once you get into these areas, but otherwise they will not convey much insight. So once again, the most important theorem, I would think, for Jun-Shao, as far as AIC is concerned, are those two, when there's no correct model or a unique correct model. A unique correct model would mean the most complex model, because any more complex model would also be true. Look at this term here. In the expansion that I showed you, there was this term. The expansion was of the penalized log likelihood. It began with norm of n squared by n plus ln alpha plus this third term plus something which was smaller than ln alpha. If lambda n equals 2, then this becomes little smaller than ln alpha, because roughly speaking, sigma n squared is like sigma squared, and lambda n is equal to 2. So this term disappears for Akaiki. It does not disappear for Akaiki, so you have to have additional conditions which ensure those conditions would have to be on this coefficient lambda n and also this ln alpha. This should not be too small, things of that kind. But as I said, that's not a good theorem to have. Once you have this decomposition, it's clear that in this context, Akaiki is the right thing to do, not these other theorems that are sort of forced. If P is fixed and n goes to infinity, then even with prediction loss, Jun-Shao showed that BIC does well. That's a nice natural theorem which everybody expects in this area. Anybody who's worked on BIC would have known that that ought to be true. So let's see what I get from there. What I'm going to do now, so the British probabilist who, here's his name, Whittle, and it's an old inequality in theory of probability and applications, the Russian journal. So what I'm going to do now is to spend more time on one particular example. I regard that again as a toy example, but this toy example is sufficiently general that will take care of the Jun-Shao examples in all generality, but the calculations are very simple. And even though it's a toy example, the calculations are very non-trivial this time. It has a little history, so you should see these. What I got here is something about Mervyn Stone. There are two very well-known stones, Charles Stone and Mervyn Stone. Charles Stone has also worked on model selection, splines and so on, non-parametric regressions. Something that is often used in data mining, these cards. So that's also due to Friedman, Jerry Friedman, Stone and others. But this Mervyn Stone, I believe, is a Bayesian, but he does frequentist things too. And one of the things that Bayesians know about, some Bayesians know about, is the problems with improper priors, and they have things like marginalization paradox and so on. But anyway, in the model selection literature, he's more well known for introducing cross-validation, which is asymptotically the same as AIC. In 1979, immediately after Schwarz's paper, I didn't follow what happened. It's only in the last couple of years that I followed what happened after that. There was some controversy. Akaiki replied back to Schwarz saying that there are cases where his thing should do much better and BIC should not be used. And Mervyn Stone, who should have known better, gave what's something like a counterexample to BIC in those contexts. It's just, I hope there's no friend of Mervyn Stone here. I regard that as an outrageous counterexample. Okay. So this toy example is his counterexample. He shows that BIC can be badly many times when you look at these automatic methods, even automatic Bayesian methods, people have been trying to calibrate them by comparing with frequentist ideas, like consistency or frequentist confidence intervals and so on. And one notion that has been used in the literature on model selection has been consistency. So what Mervyn Stone did was, for a particular example, he showed that the BIC can be very inconsistent. That is, for most parameters, it will be inconsistent, whereas the AIC will not be. And he said that in these are problems where the dimension is very large. And he said that their BIC should not be used. So that was right, but I'm going to... I should not have said that it contains an error. The point that I'll make in a moment is that the BIC is not an approximation to the Bayes factor in such cases. So it should not have been used anyway.
It violates the regularity condition.
Right. You should have used something else. I'll show you what should have been used. Here's Stone's example. Stone's example, only sort of slightly simplified, but not essentially. So it's basically Stone's example. So think of this again somewhat like the regression problem, but it's more easily thought of as one mean versus, that was Stone. So not one mean, but no mean versus, zero mean versus K mean. So I had thumb up here. Should be zero mean. So there are K means or K populations, if you like. Those are like those regression variables. You can write these in a regression form with a little effort. This is one of Junshau's examples. There are three special cases of that general model that he works through in great detail, and it's one of those also. So the Yij is the jth replicate from the ith population. So they have a common mean μi and some error epsilon ij. Once again, to avoid unnecessary irrelevant complications, I assume sigma squared is known. And these are the two models. So in one case, all the means are zero. That's the simpler model. And in the other case, all the means are sort of arbitrary, or you might say that they're not in general zero. Then the BIC looks like this. R is the number of replicates from each population, and N is R times P. So you sort of see that N has now got entangled with the dimension of the parameter, and I will not show you the inconsistency argument. It's very easy. I mean, the object was merely to show that BIC doesn't do well.
BIC or P is fixed?
BIC?
P is fixed.
The
approximation of P is fixed.
No, the derivation of Schwarz was for fixed P n going to infinity, but in the literature, BIC has been used in all cases. So in particular, in the theorems that where lambda n is not equal to 2, Junshau has theorems where P goes to infinity, n goes to infinity, and he does use BIC. So that, even though there's no reason why one should use BIC in those cases. There are other problems. I mean, Apart from the fact that it's not, when p goes to infinity, as in this example, the Schwarz proof breaks down, but that's not the only problem. There's a more trivial problem that in regression problems, you don't have IID. And the Schwarz proof was based on IID. The same proof works also for regression problems if p is fixed, but then you don't get n. You get a penalty depending, as you expect, on the determinant of the regression variables. So the choice of n was wrong. So even if p is fixed, you should, in regression problems, when you use BIC, you should be more careful. But probably this was a paper written immediately after Schwarz, so these things had not been transparent at that time. This point has been made by the group at Carnegie Mellon, Bob Cass, Larry Wasserman, and one of the students whose paper has appeared in Biometric, I think either 98 or 99. Either 98 or 99, there are 3 model selection papers in Biometric indicating the new interest in these areas. And one of them is by Gelfand is a paper like Professor Zellner's, a balanced loss function, goodness of fit and prediction. So 2 things are wrong with the BIC in this problem. For one thing, p is going to be very large, going to infinity. And the other is that it's a regression problem, a special case of a regression problem. So the right sample size is really the replication R. It turns out in this problem, the right thing would have been R, not N. But there's more to it than that. So yeah, right. So if you ignore the fact that p goes to infinity, then this is what you should have got. If you just follow through Schwarz's argument in this particular example, then that's the penalty you get. You don't get n, but you get log r. That's very easy calculations. So for fixed p, this would be easy to prove rigorously. But if p is also going to infinity, then the remainder will be huge too. So you cannot use that. I've called these the naive BIC. I mean, the usual BIC is quite inappropriate, but this at least would, even this does better than the one that Stone used. And it has, if you look at this for some time, it tells you things which are interesting. Even though it's not right for large p, it does tell you things which are interesting to look at. So let's look at that. So I'm looking at the naive BIC, which is not rigorously proved for p going to infinity. But the coefficient is log r, which you can write in the form of n over p, log n over p, which shows, if you again think of n as a sample size and p as a dimension, you see that how it sort of uses both the dimension of the problem and the total sample size. And when we began looking at this, I thought maybe lambda n equal to 2 would have a special role. And it turns out you can get lambda n equal to 2 if you choose n and p appropriately. That means choosing r appropriately, but it does not have any significance. R becomes like e to the power 2 or something, I forget what. But as Professor Zellner says, when you think in terms of these base factors, they're related to posterior odds and so forth. The Akaiki has no role to play. It's just should not be used. If you are thinking in terms of 0-1 loss, what people call hard science, Akaiki is just not the right thing to use. It took us a while to realize that that's not the way that Bayesians should arrive at. We have to look at the prediction loss. Oh, I see. Here is the comment that I just made. Okay, so anyway, so that's okay. The problems I'm talking of are very hard, and general solutions would take many, many years, probably would still be out of bounds when both n and p go to infinity. The best results, for example, the Wall lecture this year, it's the most prestigious lecture in theoretical statistics, by, not this year, last year, by David Friedman was on some of these ideas, these P going to infinity, N going to infinity. The best theorem that I know are due to Subhashish Ghoshal, but they are not adequate for what I'm going to show. And they require very strong assumptions, and P increases very slowly, like log n or whatever. What I'm going to do now is to take an extreme opposite case. I'll make P going to infinity and hold R fixed. There also, the BIC is inconsistent. You know, you'd expect the BIC to be inconsistent in such cases. And think of the following problem. Let me just give a quick background before I show you this prior. So what I'm going to do is to look at those priors, look at their base factors, and show you something like a generalized BIC, how it looks. If you take my toy example, but introduce sigma square, and still this old toy example that I showed in the last lecture, and you're looking at the same model selection problems, mu equal to 0 versus arbitrary mu, Griffiths did some theoretical calculations, and he said that there have to be two priors, mu and sigma, and he did theoretical calculations and showed that the prior for mu should not have finite moments. And the most natural such thing is a Cauchy. So that's how we arrived at Cauchy. Jim Barger has pointed out, it's implicit in Jeffries' work. Jeffries has a theorem from which this Cauchy followed. This theorem shows the following, which is sort of counterintuitive to many people who use conjugate priors, that in this problem, n mu sigma square, if you use the standard Jeffries prior, d sigma over sigma for sigma, and a conjugate normal, n0 sigma for n0, I think n0 tau square for the normal, something of this kind, or n0 a sigma square. Then compute the base factor the way that I had shown. So, and then suppose that the sample mean x bar is very, very large. Then what would you expect? You would expect that the more complex model is true. But that's not the case. Very large x bar favors the simpler model, which is an indication of how things can go wrong if you choose bad non-subjective priors. Jeffries knew these things, and people have learned from Jeffries when they've gone about these. So naturally, the priors that I'm going to show are Cauchy priors. There's something else that I should point out. I've known for many years, at least 12 years, that in these high dimensional problems, you should not have independent priors. You put in too much prior information, which you don't have. They should be hierarchical. It's sort of now percolated to the general Bayesian community also. When I wrote this, so this particular transparency was prepared last March. So I said, I noticed that I've written the computations were not yet complete. They are now complete, and I'll tell you what they tell you. Here is the prior. It's a multivariate Cauchy of very high dimension, P. That's a prior for which has been used by, which is straightforward extension of the Jeffries prior for P equal to 1, and very extensively used by the group at Carnegie Mellon. They have often used this prior as their preferred non-subjective prior. And then the base factor has this kind of decomposition. That's the first term that you saw earlier. This CP is this quantity here. Earlier what you had was not this term and no CP. The naive BIC had R, that's the least squares error, and that was the penalty, P by 2 log R. But the correct thing involves something that seems to adapt from the data. The base factor is fascinating and fantastic. I mean, there's something very miraculous about these high-dimensional base factors. That one would have thought they would go ORI, but they don't seem to. So it sort of adapts from the data through this thing here. And I'll point out about this again later. Then there are these extra terms coming from the dimension. In our case, because R is held fixed, these are the dominating terms in the penalty. I mean, these. So you see that the naive BIC is also hopelessly inaccurate. And based on these, in a paper that we have just written, Jim Berger, myself, and Nitai Mukhopadhyay, our graduate student, we propose a generalized BIC, but it's basically this one with some changes. And with this as a base factor, the following is true. The base factor is always consistent. These have some conditions. The condition is CP should be greater than 1 over R. So you have to break up the proof of these into, if you want to prove consistency using this approximation to the base factor, you have to break up into the case where CP is bigger than 1 over R, and then when CP is less than 1 over R, or you can use a direct proof. But in any case, it turns out that that the base factor is always consistent, whereas even the Akai key is only consistent in many cases, but not always. So there's nothing wrong with the Bayesian analysis of high-dimensional problems. It's only that the BIC was inappropriate.
I'd like to mention in earlier work, we used the multivariate Cauchy prior for linear hypothesis and regression.
Right.
And the posterior odds came out to be a monotonic function of the usual S.
That's right. I think that's what Jeffries sort of realized. But if you use a Cauchy prior, everything is nice. But if you use a conjugate normal, then things are bad. Jeffries had tremendous amount of intuition about these things, as well as being a very hard analyst. In fact, when Jim Berger gave his lecture on what I have not talked about today, this fixing the constant, these are all up to a big O of 1. And some problems that Professor Zellner said, if n is not large, you would want to know that constant term also. The constant term depends on the prior. So you have to fix a prior that most people would be ready to accept as not being too knowledge dependent. Something like a non-subjective prior. And there's been a lot of work by O'Hagan, Berger, and Perich, and so on. And Jim says that if Jeffries were alive, I would not have done this. For each problem, he would think about and come up with the right prior. But now that he's not there, we have to have an automatic method. And Taposh, Samant, and I have a paper where we follow their arguments and show that indeed in the n mu sigma square, you do get the Cauchy prior, following their automatic approach. But this is, the main point here is very high dimensional. What about the other prior? Now, I don't think I have anything here to show you. Okay, so let me sort of, this is an exchangeable distribution, symmetric in the mu's, the coordinates of mu. So by Definity's theorem, if you don't know, just forget that. This density can be written as an integral of a product density. Now, Jim Berger has been pointing out for some time that for P fixed, this may not be the best prior to use for non-subjective reasons. It has a spike at the origin. This prior, especially for large P, fixed but large P, has a very big spike at the origin. Nitai had verified that. He sort of been saying, so he suggested that you should use what he called the smooth Cauchy prior, a sort of variant on these, where the mixing measure is from -half to +half. Now, the same kind of calculations can be done, and it turns out that in this case, the smooth Cauchy prior does not work. It's not consistent. So that came as a surprise to him. It came as a surprise to us also. But of these two priors, so here in this case, there are two natural choices of a Cauchy prior, what people call the Cauchy prior and the smooth Cauchy prior. And the Cauchy prior wins on grounds of consistency. As a non-subjective prior, you want things to be consistent, and it wins. Why am I showing you these things? I mean, there's a little of a digression from my main theme, which is to say things about the Akaike. Oh, I've already said something about these. This log BF21 does not belong to the class of rules considered by Jun-Shao. Even these generalized BIC does not belong to his rules. Then we are going to look at this worst case scenario, R fixed and T goes to infinity. I've already said that this is consistent for all cases. I should have been more precise. This is the precise version of the consistency theorem. Either you know that the mean is 0, or you know that limit of this is positive. So that's the precise version of the consistency theorem. If the more complex model is true, you do need a condition on the mu's, they should not be too close to 0 in this sense. These are now written up, so if you wish, I can leave that paper. I'm sort of coming to the climax of today's lecture, 2 lectures. I've already said it's a special case of Jun-Shao's examples, so let's see what happens applying his theorem solved by direct calculations. These are new theorems. And I'm going to, for some reasons, which I'm going to tell you perhaps later, I'm going to look at a case where the more complex model is true. I've taken R fixed. It doesn't matter where you fix R, but I've just taken R equal to 1. And I'm taking this limiting value to be between 0 and 1. Then it's easy to show by very easy direct calculations that the oracle will choose the simpler model. Notice that the more complex model is true because 1 over p summation mu I squared is not 0, it converts to tau squared. The reason that I've chosen tau squared between 0 and 1 is to ensure that this happens. That oracle, even though the true model is the more complex one, the oracle chooses the simpler model because from the point of view of predictions, that's better. What about the Bayes factor? The Bayes factor has no chance of choosing alpha and L. I've already told you it's consistent. The Bayes factor is consistent. We know the more complex model is true, so the Bayes factor will choose the more complex model. So the probability that it will choose the oracle tends to 0. I'll come back and say that there's nothing to worry about for Bayesians. The third theorem has actually, the third result actually has 2 theorems written together. I had problems with transparency. I didn't have any extra one, but I'll show you the full thing again later. Just ignore what's written in green ink. So ignore what is green ink, then you have one theorem, and it says the following. Here is a constrained Bayesian problem. Once you choose a model, you have to use a least square estimate. Otherwise you cannot compare with Jun-Shao or oracles. So you choose a least square estimate. Sometimes that might be reasonable. You might want an unbiased estimate for whatever reason. Then this theorem says that I'm still talking about this Cauchy prior. So when I talk about a prior, I'm talking about the Cauchy prior. This does require lots of computations. So this says that the Bayes predictive rule will not choose the more complex model. It will choose the oracle. So why was this difference between the Bayes factor and the Bayes predictive rule? Because the loss functions are different. In one case, you want to know the truth. In the other case, you want to make the best predictions. The next theorem makes this further clear. Suppose you were a full-fledged Bayesian. You did not have this constraint. So once you choose a model, you use the appropriate Bayes estimates. Then you do better than the oracle. And the final explanation is very simple. This is what's going on for Akaike and has been a puzzle to all Bayesians for many years. The in some cases, you should not use unbiased estimates, but shrink. But if you sort of constrain yourself only to use least squares, the only way you can shrink is to choose a lower dimensional model. So that's what Akaike does. It chooses a lower dimensional model to shrink estimates. But if you are allowed to choose Bayes estimates, what this theorem is saying is that in this case, 0 less than tau square less than 1 is going to, you'll first choose the most complex model, then choose the corresponding Bayes estimates, and that's going to do better even than the oracle. It's all asymptotic, but this asymptotic should be fairly good because there's an n underneath, so this should be attained fairly easily. There's another theorem which is exact, which is not asymptotic, not shown in the transparencies, and that's that if you use an empirical Bayes sort of thing, that means take the mu's to be normal with some variance and choose the variance from the data. It's an old classical method, somewhat along the lines of Professor Zellner, but of older vintage. If you do that, then the Bayes rule is exactly equal to Akaike. So if you are empirical Bayes, then you are exactly doing Akaike. For other Cauchy priors, it's only asymptotically and approximately true, but empirical Bayes is exact. I'll show you these two things again in the next we're getting it late, but I suppose I'll sort of finish these. So here again, these two Bayes procedures. One is a constraint prediction, where once you choose a model, you are forced to use the least square estimate. So that's the decision problem. Your action space is to choose a model, and then it's like a baggage. Once you choose a model, the least square estimate comes with that. In the other case, you just choose a model as well as an estimate. And the theorem says, here is a sort of more precise version of what I was saying. So if it's a constraint problem, that if the more complex model is true, not just 0 less than tau square less than 1, the Bayes rule is asymptotically equivalent to AIC and Jun-Shao. When I talk about the Bayes rule, I mean for the Cauchy prior, but one knows what other priors would satisfy those. There's a sort of nice equation that has to be satisfied, and many priors would satisfy that. And but suppose you have the unconstrained problem, then under M2 the Bayes rule is better asymptotically. So, but we still assume that, remember what Akaike had said, that either the true model is not in a model space or the more complex model is true. So it's that scenario. We know also what happens under M1, but I will not show you those. It's nothing very surprising and nothing bad for the Bayesians. I have a proof of these, but I don't want to show these. Maybe I'll show you tomorrow. I have something else that I want to sort of summing up what's all about. So here are conclusions, lessons, conjectures, open problems. So the first thing is the loss is very important. Are you doing hard science or are you doing soft science? And as you would expect for each of these, the Bayes rule is optimal asymptotically. There's no sort of contradiction with frequent dispositions. What about priors? Should not be IIDs. You need some exchangeability in the mu's. IIDs put in too much information. It's easy to show that you would not get consistency. Empirical Bayes is fine because it's data dependent and does not put in that much of prior information. I'll ignore these. That was a question that it's not strictly relevant to what I'm saying, but it's interesting. Since the late 1980s, there has been some controversy, not controversy, some problem relating to AIC, not by Bayesian, but by frequentists. For example, Bryman, then who else? David Friedman. They've been saying that in the usual all subsets regression problem, and here is a typical case, n is like 50, p is like 6, so you have 2 to the power 6, they are of all subsets is of the same order of magnitude. They've been saying that you should increase the penalty from 2 to something more. It's based on their intuition rather than anything else.
For lambda n's.
For lambda n. Bryman has a couple of papers, one in JASA and I think 2 in the IS review. I have not read those, so I don't know what's there. He has, I think in the JASA paper, he does what's called small bootstrap to estimate lambda n. David Friedman has not written anything, but there's a paper by Colin Mallows in Econometrics, where Mallows also addresses similar questions. Again, I've not read those papers. But on the other hand, in the theoretical paper of Junshao, who was aware of, must have been aware of these, he does write that there are only 2, at least asymptotically, there are only 2 options. Either make lambda n go to infinity, or make lambda n equal to 2. But it might be that to settle these questions, you need different arguments. I mean, asymptotics may be too crude to settle these questions. But that's just one other aspect. What I've said throws no light on that. Okay, finally, something that I've said again, but maybe sort of mention this as a sum up. The BIC is an approximation to the Bayes rule for 0-1 loss, so it should not be used for other loss functions. It should not even be used when the assumptions for its approximation to Bayes factor breaks down. And don't use naive approximations. So in many of these cases, when you sort of complete a study, you realize that probably the Akaiki is not the best thing to use. But it has one advantage that Bayesians do not. The empirical Bayes prior that one has to choose is somewhat contextual. I've described the empirical Bayes prior for Junshao's example. If I give a lecture tomorrow, I'll explain there, what you see here, the empirical Bayes prior that I described was very natural. It's like the Cauchy prior, there's exchangeability. It's a very natural thing to use. But in Shibata's example, you would expect that most of the variability would be taken by the first few orthogonal polynomials, the first few Fourier coefficients. As you go along, they would be decreasing. That means that if you think in terms of these mu's, the first few mu's would dominate and the later mu's would be smaller. So you cannot use the same kind of empirical Bayes. And so a Bayesian can do better, but then he has to use the context also. Archaic is a very simple thing that seems to work wonderfully in these prediction problems.
Can you just give slight insight when you are giving the decomposition and the archaic term is coming in? For the approximation, what are you doing?
Well, it's just a breakup of quadratic forms. So
there is nothing deep going on in this?
Nothing deep going on. I've also checked, after looking at Junshao's, that the decomposition in Shibata is basically the same. There's a decomposition in Shibata also, written in a slightly different way, but it's basically the same decomposition.
Sir, I have one question. I'm not able to follow what you mean by one true model and many true models.
What one?
True
What?
models.
Oh, many true models. Let me give an example. We are looking at nested cases.